Hi, hello, welcome to Vision classes. It's classes for IGCSE student. We have student across more than 6 countries. So today we'll discuss the one of the important topic of A-level physics, capacitance. So we'll firstly deal with the theory part, and then we'll discuss one of the interesting question from past year paper, that is May-June 2021. Okay, so capacitance, we have to discuss the what is capacitance, what's its concepts behind it. Okay, so how it is used, then nextly series and parallel capacitance, then energy stored or work done by the capacitor. Then we have to discuss the charging and discharging of capacitors. Okay, let's move on to concepts. First one, capacitor. Now look at this here, right hand side. These are the positive, negative plates. So here plates, and this is insulator in between the two plate insulator. So here capacitor as an electric component that stores the charges on the two separated metallic plate, and an insulator sometimes called a dielectric. So this is here in between, this is dielectric material is there. Okay, it is placed between the two plate and prevent the charge traveling across the gap. Okay, so let's say C is a capacitance. It is defined as charge stored per unit potential difference across the two plates. Okay, so here these are the means positive, negative plates, and dielectric material exists between the two metal plates. So capacitance is nothing but charge over potential difference. Okay, and we have a unit for charge is coulomb, then unit for potential difference is volt, and we have a capacitance unit, that is Faraday. Okay, so microfaraday is 10 raised to negative 6 Faraday, right? Then nanofaraday is equal to 10 raised to negative 9 Faraday, and picofaraday is equal to 10 raised to negative 12 Faraday. Okay, so in example, sometimes they use this unit, so you must know the units of capacitance. Okay, then nextly, so capacitor actually here positive plate and negative plate. So dielectric material is exists between the two plate. Fine. So when the capacitor is connected to the DC power supply, means that's a battery. There is a brief current as a power supply drawn the electron from a one plate and deposit them on other plate, and this leaves the first plate with the charge Q. So this is positive charge. Okay, and second plate with negative charge. Okay, negative charge, and this charge will be equal and opposite due to conservation of charges. Okay, so that is why generally it is said that means capacitance actually stores the energy rather than charges, because this two plates actually separate these charges separately. Okay, separately in a sense, this left hand side metal plate actually stores the positive charges, and right hand side metal plate actually stores the negative charges. Okay, and there exists the dielectric material between these two metal plates. Okay, so when this actually charges travel, let's say positive charges travel within this circuit. Okay, and when circuit will be completed, that is when work is done. Okay, so that is why it is again said that energy is stored rather than charges. Okay, in the capacitor. So current flow in the circuit until the potential difference between the plate is equal to the electromotive force EMF of a power supply. Okay, means the actually the charges are actually supplied till they become equal. Fine. So this is working of just a capacitor, real capacitor or real battery. Now capacitor having dielectric material, right, present between them. So its purpose to increase the capacitance of a device by polarizing the electric field and effectively increase the charges stored on the plate. Means just increasing the capacitance of the device, and the dielectric has an associated electric permeability, which describes the ability to polarize or strengthen the charges to charge stored ability of a device. And this is why in reality actually insulator is really in the vacuum, and just air as a material do not polarize well, so are the poor dielectric. Okay, here positive plate and this one is negative plate. So positive Q and negative Q, dielectric between material exists between the two plate, right? And this dielectric material actually increase the capacitance of the device. That is what it does. Okay, so nextly, applications of capacitors. So capacitor generally used to store and discharge large quantities of energy in short period of time. For example, camera flash, touch screen, short finger press lead to the large built up energy in the capacitors. Okay, even nextly, the integral to the uninterrupted power supplies or UPS, right? UPS are commonly found in data center to protect the hardware, in the hospital to maintain the constant power supply. Okay, finally, generally capacitors are used to convert in the AC current to DC current. Okay, and yes, these are the just applications of capacitors. So positive Q, negative Q, and this is plate. Okay, then nextly, work stored or work done by the capacitor. Let's say here work done by the capacitor is nothing but negatively charged electron move towards the, so work done by the power supply to deposit negatively charged electron into the negative charged plate, like charge repel according to Coulomb's law. So work done to move electron from a positive plate as negative charges are attracted to positive region. So see, simply work done is nothing but when positive charge Q move towards the negative charge, and this one is, and this y-axis is voltage V, and Q are the charges along the x-axis. Charges, when positive charges move towards the negative charges, and that is when the work is done, right? So the graph shows the charge stored on the capacitor plate against the potential difference over the device, as voltage is defined as the electric potential energy per unit charge area under the graph, therefore represent the work done in charging capacitor. So energy is stored in the capacitor, which is equal to E is equal to 1 over 2 QC. Okay, so this is just a area of this triangle. Okay, so this is the area of triangle is 1/2 Q over C, right? Energy stored in the capacitor, and we have a C which is equal to Q over V, right? So we'll use this formula, modify energy equation. Look at here. If you put here C, you will get 1/2 Q square over V, right? And if you put instead of Q as a CV, right, you will get 1/2 C square V. Getting it? Means we have a 3 energy equation which is equal to 1/2 Q C square is equal to 1/2 Q square V, or which is equal to C square V. Okay, so that's a work done or energy stored in the capacitor. Then nextly, capacitor in series and capacitor in parallel. So we have to just discuss here derivations, and it's a very interesting actually, because a number of times they ask the question on this indirectly, not directly as such. So C1, C2, C3, okay, here capacitors are there. When they are in the series, actually potential difference across the capacitor is different. Okay, means here at a C1 potential difference is V1, at C2 potential difference is V2, and at C3, potential difference is V3. Okay, so positive, negative, positive, negative. And when this charges are same. Okay, so here we have even earlier discussed that C is equal to Q over V. Okay, just we'll rearrange this formula. Q is equal to C V1. Okay, we'll rearrange here formula. V is equal to Q over C, right? So here the total voltage across this capacitor in the series is equal to V is equal to V1 plus V2 plus V3, means total potential difference is across this capacitor in the series, which is equal to V1 plus V2 plus V3. Okay, so here V1 is equal to Q over C1. Likewise, V2 is equal to Q over C2, and V3 is equal to Q over C3, right? Then just to put out in this equation, we know already V is equal to, potential difference is equal to Q over C, that is equal to Q over C1 plus Q over C2 plus Q over C3, right? So just take a Q out and just cancel out, because on the left hand side we have a Q, right? So Q over C is equal to Q, take it out, so you will get 1 over C1 plus 1 over C2 plus 1 over C3. This Q get cancelled out, and you have final derivation for capacitors in series is equal to 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Getting it? Right. So nextly, capacitors in parallel. So potential difference across the capacitor in this case is same. Let's say here I will name it firstly C1, C2 and C3. Okay, and here in this case positive, negative, positive, negative, right? And then charges are different. Okay, means charges at C1 is equal to Q1, charges at C2 is Q2, and charges at Q3 is C3 is Q3. Okay, so again same formula, just C is equal to Q over V. Okay, so here charges are different. Here Q, just rearrange this formula. Q is equal to C times V, right? So total charges across the parallel connection is nothing but Q is equal to Q1 plus Q2 plus Q3, right? So we have a Q1 is equal to V C1, right? Q2 is equal to V C2 plus, not a plus here, Q3 is equal to V C3. Then just put in this formula. So Q is equal to CV is equal to C1V plus C2V plus C3V. Just to take V out, CV, V is equal to C1 plus C2 plus C3, right? And just cancel out this VV. So total capacitance across the capacitor in the parallel connection is equal to C1 plus C2 plus C3. Okay, that's it. Getting it? Right. Then nextly, so capacitance and current relationship or relation. Generally, see, we have a capacitance is C is equal to Q over V, and we have a formula for current is equal to Q over T, means charges, rate of charges passes through the circuit, right? So yes, we can just correlate here. If this Q, just rearrange these terms here, Q is equal to IT, and put this Q in the capacitance equation. So you will get C is equal to IT over V, right? And if you want to find out this I, just rearrange the term and you will get I is equal to CV over T. Okay, these are the two formulas you will get. Getting it? So this is just a relation between capacitance and current. Okay. Now, nextly, we have a charging and discharging of capacitors. Actually, capacitors are the nothing but batteries, right? Of course, when we connect to the electricity circuit, or when which passes the charges, it will charge, right? And when we use for some application or some device, yes, to run something, capacitor discharge, right? It's all charges are passes through the application purpose, isn't it? So in those cases, actually this charging and discharging actually happens in the exponential manner. Means, so look at here, one, okay, means initially fast, okay, and then slowly charges. Okay, so this is charging and discharging. This is charging and discharging is like this one. So it charging and discharging exponential graph. Discharging, right? So we have to write down the equations for the charging and discharging of, let's say, current, voltage, and charges. Okay, current I, then voltage V, and charges Q. Getting it? So exponential here, exponential decay means just a relation between this x-axis graph and y-axis graph. Okay, so this is actually on the x-axis we take a time, and on the y-axis we take a capacitance. Okay, capacitance. So here exponential relation is actually x is equal to x0 e raised to negative ky, e raised to negative ky, and this x0 is actually x0 and k are the constant, and x and y are the dependent and independent factor respectively. Okay, so generally if you have a, let's say, x-axis, and you can find out the y-axis easily. Okay, so yes, these are the exponential graph of charging and discharging. Now for a current, we have a I is equal to I0 e raised to negative T over RC. So this RC is constant, and T is a time, I0 is a initial current. Okay, then for a voltage, V is equal to V0 e raised to negative T over RC. Okay, and here also same, RC constant, T is time, then V0 is initial voltage. Okay, for a charges, Q is equal to Q0 e raised to negative T over RC, right? So these are the relations are there. And for a A level, actually you don't need to remember whole derivation part. Actually, that's the main thing. You just remember this, how to use these equations for an example or in the example. Okay, so if question comes like this, means this RC factor is given, time is given, and initial voltage is given, then if they told us to find out the voltage, then you can use this equation, voltage equation. Getting it? Right. So final potential difference in the battery. Okay, you can calculate through this formula. Okay, then at the end we have another formula, which is actually capacitance is directly proportional to the area, capacitance C directly proportional to area, and capacitance even inversely proportional to the distance between the two plates. Okay, so these are, let's say, two plates here. Okay, and it is connected in the circuit, right? So this is distance between two plate is d, right? So in this case, capacitance is directly proportional to area, and capacitance is inversely proportional to the distance between them, right? So the capacitance of a two plate is nothing but A over D. And to remove this proportion, we use the proportionality constant, that is epsilon, okay? Epsilon A over D. And there is another constant, relative permeability of dielectric medium between them. Actually, this part here, dielectric medium is exists, right? So we have to take the constant while calculating capacitance. So here, permeability and relative permeability, ER times A over D. This is the capacitance of a capacitor, okay, for a generally parallel plate capacitor. Okay, so in some example, actually this formula is used. That is why I am discussing, and I hope it will help you. And these are the just a part are there in your capacitance chapter. Okay, yes, that's it. And then we'll move on to one example of a past year paper. Fine. If you have any doubt regarding this capacitance concepts, I have left my contact number in the description box. Even we have started revision classes. So if you want to connect with us, then you can connect me directly through the link I have given. And even we have developed our website. We are just providing there free of cost video classes, lectures, even some of the theory materials. So you can directly go on to our website, visionigcsc.com. Okay, it's our website. Okay, so right, we'll move on to past year paper. So it's a May-June 2021 question paper. Look at here what it says. State what is meant by the capacitance of parallel plate capacitor. Okay, here's this. So parallel plate capacitors, as I told you earlier as well, what's the same in the parallel plate capacitor and what's the different in the parallel plate capacitor? So in the parallel plate capacitor, we have a potential difference across the, it's the same, right? Potential difference is same, right? Across the whole circuit, and charges are different, right? As Q is equal to Q1 plus Q2 plus Q3, right? So what does it mean is that charges are different, right? Different. So you can just add here a potential difference same across the circuit. Okay, so V is same across the whole capacitors, and charges are different across the different capacitors. Okay, so these are the 2 points. You will get the 2 marks. Okay, then nextly here in a sub question of 7, it says that capacitor of capacitance C is connected in the circuit, right? Here capacitance is connected, then sensitive ammeter is connected, then a two-way switch, a position A and B capacitor charged so that the potential difference across it is V. The switch moves the position B, okay, and capacitor fully discharged through the sensitive ammeter. The switch moves repeatedly between A and B so that the capacitor charged then discharged with a frequency F. Okay, show that average current in the ammeter is given by expression. So we just we have to show this equation, I is equal to F times C times V. So we at the end we have discussed a capacitance and current formula. So recall those formulas here. C is equal to Q over V, and I is equal to QT over Q over T, actually, right? That's what we have discussed, right? So Q is equal to CV, and put in this equation here. So you will get I is equal to CV over T, and we know that sorry, T is equal to 1 upon F, and F is equal to 1 upon T frequency, right? So I is equal to F times CV. Okay, that is what you will get at the end, right? Getting it? This is just a derivation part. So you just have to use the relation between capacitance and the current. Okay, that's it. Then nextly, what's a third sub question? The potential difference V is 150 volt and frequency is 60 hertz. Average current in the ammeter is 4.8 microampere. Calculate the capacitance in the capacitor. So here we have to calculate the capacitance, have a relation I is equal to F times C times V, right? So just rearrange this equation as a C is equal to I over F times V. So I, we have a 4.8 times 10 raised to negative 6, or voltage is frequency is 60 times voltage is 150, right? And you will get, when you use the calci to calculate this part, 4.8 divided by 60 times 150, you will get answer 5.33 times 10 raised to negative 4 times 10 raised to negative 6. Okay, so here here picofarad is unit they have written, so you have to convert this also in negative picofarad, right? Pico to farad means negative 10 raised to negative 12. Okay, so you will get this as a 10 raised to negative 10. Okay, so just shift this 2 point, right? So it's a 533 times 10 raised to negative 12 picofarad Faraday. So just write down here 533 picofarad. It's nothing but 533 times 10 raised to negative 12 Faraday. Getting it? Means you just have to adjust a little bit to get 10 raised to negative 12. Fine. Then in the last part, actually, the second capacitor having same capacitance as the capacitor in B, right? So capacitor as in B, right? In the circuit, and two's connected in the series. They said here series, right? So series means you just have to firstly find out the capacitance in the series, and we have a formula for series connection. We have discussed a formula: 1 over C is equal to 1 over C1 plus 1 over C2, right? So we will just take a here 1 over 533 plus 1 over 533, which is equal to 1 over C is equal to 2 over 533, right? So C is nothing but just a reciprocal of 533 divided by 2, which is equal to 266.5 picofarad. Okay, this is not answer. This is just a capacitance you got when you connected, when you connect the capacitors in series, right? Then nextly you have to find out the current. Current I is equal to F times C times V. Okay, so F we have 60 hertz, right? And this 2.66, no 2.6, not a 266.5 picofarad, right? Times 10 raised to negative 12 times 150 volt, which is given in the earlier question. Okay, so when you solve this whole thing, and you have to put this equation, this answer in the microampere, because they already said here you have to put this into the microampere, right? So here 266 times 60 times 150, which is, if you multiply here 10 raised to negative 12, you will get 2.3985 times 10 raised to minus 6. Okay, and that's nothing but 4 microampere. Okay, that's a current. So your answer will be 2.4 microampere. Fine. So this is how you have to solve this step-by-step equations. Getting it? Yes, that's it. If you like this video, share with your friend and subscribe to our channel for a more update. Okay, we have already started revision classes for IGCSE and then AS and A level for May-June 2022 exam. So if you want to connect with us, you can contact me directly. I have left the link in the description box. That's it. Bye bye.